We will spend some time on matrix multiplication because it is very important. The basic definition of a matrix multiplication: when you have matrices A and B, multiplying them, you will get a product C. And the first definition, we will use a row-column kind of multiplication. So let's take an example first. We have our A in red and B in blue. What we will do is to take the row of A and the column of B and go in those directions, and we will do some product operation. That will be one element of the product, but where will that go? So this was the first row, first column, so that will go to the first row, first column of the product. So C will be AB. So the first row of A, 1 and 3. First column of B, -2 and 3. Some product, and that becomes the first row, first column element of C, the product. Let's take the last one here. So that will be the second row of A and the second column of B. 2 times 0, 2 times 0, 1 times 7, and that goes there. So as you can see, the number of columns of A will have to be the same as the number of rows of B. Otherwise, this multiplication cannot work. The number of columns of A will have to be the same as number of rows of B. So let me say that once more. You're going this way across the columns of A and down the rows of B, multiplying element by element, and then each element in this horizontal travel will have to have a corresponding element in the vertical travel. Otherwise, you will not be able to do the multiplication. So number of columns of A, same as the number of rows of B. So you will write matrices like this: M by K and K by N. So the inner ones, the number of columns of A and the number of rows of B, will have to kind of cancel each other to get M by N. So a matrix in R M by K and another one in R K by N can multiply and give you a matrix in R M by N. The inner ones get eaten. So the matrix multiplication is associative, but it's not commutative. So even from the basic conformance requirement, you can see that commutativity cannot work. So we saw that the inner parts of the dimensions, the number of columns of A and number of rows of B, will have to be the same. So if both of them are square matrices, of course conformance is okay both ways, AB and BA, conformance will work, but still the product will be different. In general, there are special cases when the products are the same. Can you tell me a couple of special cases? Let me give you a few. If A is the same as B, then A times A is A times A, so that is fine. When A is the identity matrix, which is the same as number 1 in the case of numbers, so I times A is the same as A times I. That is another one. And of course, if one of the matrices is a 0 matrix, then the product is always 0. So A times 0 is 0 times A. Of course, conformance has to be satisfied. That means all these matrices are square matrices that I'm talking about. Then the products can commute in these special cases. There is one more special case that will come much, much later. I may forget to actually highlight to you then. Let me just say it now. If the matrices have the same eigenvectors, then they can commute in multiplication. I'll just leave it at that. Don't worry too much about it because we are very far away from doing eigenvalue decomposition. But I just wanted to keep it there as a placeholder. Okay, now the thing is, the product AB, as we define here, that is what we will call the row-column definition. But we can also think of it as linear combinations of the columns of A or the rows of B, and also blockwise multiplication, etc. So there are different things to look at here, which is why this section is going to be a bit heavy. So first of all, the row-column picture. So what you will do to get C11, AB equal to C, that's our product. C is a product. To get C11, go across the columns of A along the first row, go down the rows of B along the first column, and that will give you the first row, first column element of the product. The row coming from the first matrix, column coming from the second matrix. In order to get C22 there in blue, second row of A, second column of B. In general, in order to get the ith row, jth column element of the product C, go through the ith row of A and the jth column of B. So this somehow you have to get used to. And this implies the conformance requirement that the number of columns of A will have to be the same as the number of rows of B. Now there is a column picture which is actually very interesting and very, very useful for the rest of the course. Now take any matrix with m rows and n columns. Think of this matrix not as elements inside, but as column vectors. So it's got n column vectors because it's got n columns. Each vector's got m elements. Let's multiply by some vector x in Rn. So Rn means it's got n rows. So the columns of first matrix A is the same as the rows of the second matrix X. So that multiplication can work. And now what I'm saying is that this product is a linear combination of the columns of A using the numbers in X as the weighting factor. So let's take an example. I have my A here and my X there. So I have the first vector, second vector, third vector, and fourth vector in A, which will get multiplied by the corresponding colored squares in my X vector. So C1, C2, C3, and C4 will get multiplied by 3, 5, 2, and 7 respectively. And that linear combination, because C1, C2, C3, and C4 are just vectors, and that linear combination is the product. And of course, the conformance requirement is satisfied because the number of columns of A, 4, is the same as the number of rows of X, which is 4 also. So the product will have a 3 by 1 shape, 3 rows and 1 column, which also is fine. So let's do this step by step. I have my 4 columns there, C1, C2, C3, C4 multiplied by 3, 5, 2, and 7 respectively. So I get AX equal to 3C1 plus 5C2 plus 2C3 plus 7C4, all color-coded for your reading pleasure. So I just plug in the numbers, add them up, and finally you get 56, 104, and 102. And you can verify this by doing a row-column kind of multiplication, each one separately, and you will get the same thing. Now we can extend this column picture to multiple columns in the second matrix. So the first example we did, we had only the red column, the first column in B. Now let's add a blue column, the second one. Again, the product C will contain columns that are linear combinations of the columns of A weighted by the corresponding columns in the matrix B. So now A has 3 rows and 4 columns, and B has 4 rows and 2 columns. So the product C will have 3 rows and 2 columns. The first column of the product will be a linear combination of the columns of A with the weights coming from the first column of B. The second column of the product C will be again linear combinations of the same columns of A, this time coming from the second column of B. So what you have to remember about the column picture is that the product will contain the linear combinations of the columns of the first matrix weighted by the elements in the corresponding columns of the second matrix. So columns everywhere. The first column of AB, linear combination of the columns of A with the first column of B as the weights. The second column of AB, linear combinations of the columns of A, the same columns of A, but the scalars coming from the second column of B. Similarly, the transpose case of that will be the row picture. This time, I'm going to say that X transpose is the first matrix and A is the second matrix. Just to be consistent, the X transpose A matrix will be a linear combination of the rows of A because A is a second matrix. So what kind of a linear combination? A linear combination with the weights coming from the row of the first matrix. So again, I have the rows of A, R1, R2, R3, R4 with the transpose because they're rows, not columns. And multiplying them will be the corresponding elements in the row of X1, the first row. There's only one row. And that would be 7 for red and 1 for blue, R2, and 1 for green, R3, and 4 for purple, R4, which is 7, 2. So let's take that linear combination, 7 times R1 plus R2 plus R3 plus 4 times R4. I'm dropping these transpose things in my diction, my delivery here, so that I can say it easier. So 7 times 3, 4, 1 times 5, 1, 1 times 2, 3, and 4 times 7, 2. 4 times 7, 2 here. Expand it, add them up, you get 56 and 40. So multiplication on the left is the same as taking the linear combinations of the rows of the second matrix, A in this case, and the coefficients will come from the elements of the first matrix on the left from the row. And if the first matrix has multiple rows, just like we did it for the column picture, each row of the product will be linear combinations of the rows of the second matrix by taking the weights from the different rows of the first matrix. I know that these things will take a little bit of time to completely sink in for you to get the hang of, but you will get there, don't worry. So now I have the same two matrices, A and B. This time, instead of looking at it from the perspective of column picture, whereby I had the columns of A being weighted by the columns of B, I'm looking at the rows of B, the second matrix, weighted by the rows of A, the elements in the rows of A, and that will look like this. AB equal to C. A has 3 rows and 4 columns as before, B has 4 rows and 2 columns, and C will have 3 rows and 2 columns. In fact, A and B are the same matrices as before, so C will have to be the same product, but we're just looking at it differently. Right, so linear combination of the rows of the second matrix B, the first row of AB, the product, will be the linear combination of the rows of B with the scalars coming from the first row of A, 7, 1, 1, 4, and 3, 4, 5, 1, 2, 3, and 7, 2, just like we saw. And the second row of AB will be a linear combination of the same rows of B, but this time taking the blue second row of A as the weights. And the third row will take the third green row as the weights for the same rows of B, which will get linearly combined. So that is a summary of all those things in one picture. Now, there is one more thing which is even fancier. It's called blockwise multiplication. Matrices can be multiplied blockwise. Matrix multiplication is defined in a kind of infinitely recursive fashion, which you will come across in many different situations later. And it is very programming language wise, and which is the reason why linear algebra happens to be the mathematics best suited for computer science and most needed for computer science. Now, the idea is that if you can segment the matrices into conformant blocks, then you can multiply them block by block. Let's start with an example. Suppose you have a square matrix A and a matrix that is rectangular, wide, like two matrices standing side by side. Then, of course, AB is going to be, these inner indices will disappear. It's going to be 2 by 2n in size. And now you can think of B as a square matrix as the first block, another square matrix standing next to it as a second block. And since they are square matrices of the same size as A, they're conformant for multiplication. And you can write AB as A multiplying B1 and B2 standing side by side. And then you can kind of expand it by saying that it is AB1 and AB2. It's because if these had been a scalar and a matrix of one row and 2 columns, that would have been AB1, AB2. This is not quite the scalable way of describing it, but you can see that in the matrix case also, it works kind of identical to that. This is what I mean by it's infinitely recursible. Now, another case is when you have A in m by n, R in n by k. You can think of B as k column vectors in Rn standing side by side. So B is B1, B2, B3 up to Bk standing side by side, which you can probably use a shorthand notation like that. Now, multiplying A is again like taking A inside into each one of those blocks. Each block now is a column vector, and this also works. Then there are other segmentations that are possible, and we will not get into all those things now, but be aware of the fact that these segmentations can lead to interesting algorithms, and people do use it. Toward the end of this course, even though we will not go through it in class, in the textbook, there is an algorithm that is described called Cholesky decomposition. And if you look at it, the proof of it, you will see that it uses block multiplication in a very imaginative way. Not merely for the mathematical beauty of it, also to save memory, say, reuse space and array locations and things like that. Very computer science kind of things that you can do. There's one more thing I want to talk about, It is in the product you have A in R m by k and B in R k by n, and the product is going to be a matrix of m rows and n columns, and they're conformant for multiplication. Columns of A, same as the rows of B, all good. And you can think of m by k as m by k, and you can kind of imagine that these guys are cancelling off. This is my mnemonic. This is the way I kind of remembered it when I first came across this. And you can write the ith row jth column element of the product C in this fashion, taking the ith row of A and multiplying it by the jth column of B, and the P, the folding index as it were, will get summed over and disappear. So that's a dot product. Now the question to ask is, how many operations are there in this multiplication? Operations can be either additions or multiplications. So per element, k additions and k multiplications for this guy, and then there are m rows and n columns. So it looks like the total number of operations will be m and k. So if all these matrices were n by n, so it's of the order of n cube. That is the computational complexity of this thing. But there are algorithms that do it at n to the power 2.4 roughly, and it may not sound like much. What's the difference between 3 and 2.373? Not a big deal. But imagine that n is like 10,000, which is not uncommon in data science. So the difference is actually going to be 1 trillion versus 35 billion or so. So that's a factor of roughly 300. That is significant. If matrix multiplication takes brute force nested for loops, it takes, let's say, 300 minutes, which is what, 5 hours. Using this algorithm, you can do it in 1 minute. Now let's move on to dot product once more. We saw that vectors were just matrices. It's a column matrix, and a row of numbers would be a transpose of a vector. So a column vector is a column matrix. Take a transpose, that becomes a row of numbers. We haven't defined transpose, but transpose is a fairly simple concept. Ask the elements in a column to lie down in a row, and that's it. Some people consider that a row vector. I personally don't like it that much. So if you come across a row vector, we'll call it a row matrix and say that is a transpose of a column vector. So if X is in Rm, m elements, then X transpose will be one row with m elements standing side by side. Now, something interesting to note is that X transpose times X, if you do the dimension counting, this m and that m will cancel, then you'll get R 1 by 1, which is R. So X transpose X is a real number, is a scalar. That is the dot product of X with itself. X transpose, on the other hand, is an m by m matrix. M by m matrix. Interesting. Now remember our dot product A and B. The red A 4 5 and blue B 3 1, and A dot B was at some product, accumulated product. Now let's say you use a row vector, take A transpose 4 5 in a row, and then B, then these two things can multiply, and that is actually just the sum product of the corresponding elements, and that turns out to be 17. So numerically, A transpose B is the same as the dot product. Very nice. So A transpose B is the same as B transpose A. Can you see that? If you take B transpose and put it on the left-hand side and take the product, you get the same number. Numerically, the blue numbers will happen here, come before the red numbers, but multiplication of real numbers is commutative, so it'll add up to 17 anyway. So we could have used just A transpose B as a definition of dot product, which is very nice. So we don't really need a special product operation, which is our dot product. Right. Now, having said that, there's one more way in which we can look at matrix multiplication. We looked at this as a row column multiplication, accumulating product element by element. But another way of saying that is some product of these guys, the row matrix and the column matrix. And row matrix is, of course, is a column vector transposed. So it's a dot product of the corresponding vector, the green vector and the purple vector. So again, the same kind of idea. A has 3 rows and 4 columns. B has 4 rows and 2 columns. And AB will have 3 rows and 2 columns. So take the dot product of the vector corresponding to a row and a vector in the second matrix, and that product will give you the element of the product matrix in the ith row and the jth column. If you take the ith row of the first matrix and the jth column of the second matrix, take the dot product, and that's how you would get it. So you can think of matrix multiplication in terms of dot products too. The element dij, which means ith row and jth column of D, is a dot product of the ith row of A, thinking of it as a vector, and the jth column of B. That is very nice. So all these things, all these special cases like dot products masquerading as matrix multiplication and a column picture, row picture, they are all special cases of the most general blockwise multiplication. It's just that we're dividing it into imaginative blocks that are conformant for multiplication. Now, this is all there is to matrix multiplication, but in computer science, you're likely to come across other operations that will not be treated in any great detail in this book because they're not quite linear algebra kind of operations, but they're matrix operations nonetheless. So there's an element-wise product called Hadamard product. So that is, if you have two matrices of the same size, not conformant for multiplication particularly, it's just same size matrix, you can think of multiplying corresponding elements and then get a new matrix. And that product is called Hadamard product. It's got some applications in image processing and neural networks, etc. Then there is this scalar addition, which is take a matrix and add a scalar, which is, if you think about it, that cannot be done at all because a scalar doesn't add to a big matrix. But you can define it in terms of linear algebra. You can say that you're taking a matrix of the same size as the original matrix that you want to add something to and putting ones everywhere and then scaling it by the scaling factor, then adding them up. So you're adding that scalar to each element of the matrix under consideration, and then every element gets biased or moved by that. So it's used in increasing biases and brightness adjustments and stuff like that. So that is another operation that you'll come across. And convolution is another operation, which is like a smaller matrix sliding over a bigger matrix to apply certain image processing filters. And that is again something that you will come across during your project work. And this is also used in a convolutional neural network. So think about these operations and see if they're actually linear. Some hints and some more information is available in the textbook. It's not as part of the main text, but as red boxes here and there. So that brings us to the end of today's lecture. And next week, we will move on to some other properties of matrices like transposes and determinants.
Thank you.